Hello everyone, I'm Professor Kang Xiao from the University of Chinese Academy of Sciences. In this section, we are going to learn the second part of membrane bioreactors, plant design, operation, and maintenance. Here shows the outline of the whole section. In the first part of the section, we have learned process composition and pretreatment of an MBR process for wastewater treatment. Now, let's have a look at the biological treatment units. The design of the biological treatment units of an MBR process mainly includes the volume of the tanks, mixed liquor recirculation routes and ratios, aeration demand, and excess sludge production. The volume of the tanks is critical to the biological treatment capacity. It is related to the wastewater flow rate and quality, sludge concentration and loading rate, sludge yield and retention time, and reaction rate of the pollutants. Therefore, the volume of the tanks can be calculated from these kinetic parameters. The mixed liquor recirculation routes and ratios should be properly designed because they can affect the distributions of dissolved oxygen (DO) concentrations, sludge concentrations, and the pollutant removal efficiencies in the anaerobic A1, anoxic A2, aerobic O, and membrane M tanks. For instance, the recirculation from aerobic to anoxic tank should be high enough for the removal of nitrate nitrogen, but not too high to disturb the anoxic environment. The DO in the anoxic zone should be less than 0.2 milligrams per liter to avoid inhibition of the denitrification process. For MBR processes with separate aerobic and membrane tanks, an adequate ratio of recirculation from membrane tank to aerobic or anoxic tank will prevent any excessive accumulation of MLSS in the membrane tank from exacerbating membrane fouling. For the aeration demand, microorganisms in the aerobic zone require oxygen for BOD degradation and nitrification, because these are oxidation reactions. The DO concentration in a separate aerobic tank is recommended to be 1 to 2 milligrams per liter. If the aerobic tank is integrated with the membrane tank, part of the DO can be supplied by the aeration for membrane scouring. Excess sludge production should also be evaluated to design the facilities for sludge discharge, treatment, and disposal. If the biological process is not sufficient to meet the effluent TP standard, chemical precipitation can be conducted by dosing chemicals into the biological tanks or in an additional reaction tank as a supplement. In such case, the design of excess sludge production should also consider the additional amount of chemical precipitates or coagulation products. Here is an overview of the steps for the design of the biological treatment units for an MBR process. The steps include the selection of process flow, design of pretreatment and primary treatment, design of biological treatment units, and design of membrane filtration system. The design of biological treatment units involves selection of design parameters, calculation of tank volumes, recirculation flow rates, excess sludge production, and aeration demand for biological reactions. Here, we take the AAO-MBR process as an example to show how to design the biological treatment units step by step. First, we need to select a series of designing parameters for the subsequent calculation. The table here lists the parameter values, which are mainly adopted from the technical specification for design of membrane bioreactor processes for municipal wastewater treatment. The detailed procedure and the equations for the calculation will be introduced hereinafter. From this slide, we are going to learn how to design the dimensioning of biological treatment units in an MBR process, taking the AAO MBR process as an example. First, let's calculate the volume of the aerobic zone. Basically, there are two methods to calculate the volume of the aerobic zone. Option 1, to calculate from the growth rate of nitrifying bacteria and SRT. And option 2, to calculate from the ammonia utilization rate and nitrogen mass balance. We should note that the volume of the aerobic zone includes the aerobic tank and the free volume of the membrane tank. Because they are all under aerated condition, this is a special point for the MBR process. For option 1, we calculate the volume of aerobic zone from the growth rate of nitrifying bacteria and SRT or sludge age. From this equation, we can see that the growth rate can be either obtained as a quotient of sludge mass and sludge age, or the product of sludge yield and the substrate amount. We note that the volume is included in the sludge mass term. Therefore, the volume of the aerobic zone can be expressed like this. Here, V denotes the volume of the aerobic zone, including that of the aerobic tank and the membrane tank, where the aerobic biological reactions occur. Q is the designed flow rate. S0 and SE are the BOD concentrations in the feed and effluent of the biological treatment section, respectively. The effluent BOD concentration is negligible when the removal rate is higher than 90%. X is the sludge concentration in the aerobic zone, which is regarded as the weighted average MLSS concentrations of the aerobic and membrane tanks. The MLSS concentration of MBR is much higher than that of CAS process because of the complete rejection of MLSS by the membrane and the longer SRT of MBR. YT is the observed yield of solids per unit BOD, which is considered to be slightly lower than that of CAS because of the longer SRT and the smaller sludge loading rate that facilitate endogenous decay. Theta is the minimum sludge age in the aerobic zone, which can be estimated as the reciprocal of the specific growth rate of nitrifying bacteria, multiplied by a safety factor F with a value of 1.523. The specific growth rate of nitrifying bacteria, μN, can be derived from the maximum specific growth rate of nitrifying bacteria, μNM, according to the monad relationship with temperature correction, as shown in this equation. Here, Kn is the half-velocity constant for ammonia utilization. MOM1 is the ammonia concentration in the aerobic zone, and T is the temperature of the mixed liquor. The maximum specific growth rate of nitrifying bacteria of MBR appears to be comparable with that of CAS, but the growth of nitrifying bacteria is facilitated by the longer SRT, and can be more resilient at low temperatures in MBR than in CAS, which can influence the safety factor of the growth rate under these conditions. It should be noted that because theta is the minimum sludge age in the aerobic zone, the volume calculated here is considered to be the minimum volume of the aerobic zone needed to fulfill the requirement of nitrification. The volume of the aerobic zone can also be calculated from the ammonia utilization rate and the nitrogen mass balance, which is option 2. Here, this equation shows the mass balance. The utilization rate is equal to the uptake rate of nitrogen from wastewater, minus the discharge rate in the form of excess sludge. From such mass balance, we can calculate the volume of aerobic zone like this. NK0 and NKE are the gelda nitrogen concentrations of the influent and effluent of the aerobic zone, respectively. Delta XV is the rate of biomass discharge from the system. 0.124 is an empirical proportion of nitrogen content in the microorganisms, and Vn is the specific ammonia utilization rate. The biomass discharge rate, delta XV, can be estimated as a product of biomass ratio, sludge yield, and BOD uptake. The biomass ratio in the sludge, also known as the proportion of volatile mixed liquor solids in the total mixed liquor solids, is typically in the range of 0.4 to 0.7 for MBR systems. This ratio is somewhat lower for MBR systems than that for CAS systems. The specific ammonia utilization rate, Vn, can be derived from the maximum specific ammonia utilization rate, VNM, according to the Monod relationship, with temperature correction as shown in this equation. In summary, we have introduced two methods to design the volume of the aerobic zone in this part. Option 1, to calculate from the growth rate of nitrifying bacteria and the SRT. And option 2, to calculate from the ammonia utilization rate and the nitrogen mass balance. Then, let's move on to the next step to design the volume of anoxic zone. The volume of the anoxic zone can be calculated from the denitrification rate and the mass balance of total nitrogen, as shown in this equation. The denitrification rate is equal to the uptake rate of total nitrogen from wastewater, minus the discharge rate in the form of excess sludge. Here, NT0 and NTE are the total nitrogen concentrations in the influent and effluent of the biological system, respectively. KDN is the specific denitrification rate, which is normally in the range of 0.03 to 0.06 kg nitrate nitrogen per kilogram MLSS per day, and XA2 is the MLSS concentration in the anoxic tank. Then, the volume of the anaerobic zone can be simply calculated as the flow rate multiplied by the HRT of the specific zone. The HRT of the anaerobic zone is normally in the range of 1 to 2 hours, which is feasible for the microorganisms to release phosphorus under anaerobic condition. Here in this slide, we design the mixed liquor recirculation routes and the recirculation ratios between different tanks, taking the AAO MBR process as an example. Firstly, the mixed liquor in the anoxic zone is normally recirculated to the anaerobic zone at a ratio of 1 to 2. An excessively high recirculation ratio will shorten the real HRT for anaerobic phosphorus release and also disturb the anaerobic environment because the anoxic mixed liquor contains electron acceptors such as nitrate. Secondly, in order to enable biological denitrification to remove total nitrogen, the mixed liquor in the aerobic zone needs to be recirculated to the anoxic zone. The recirculation ratio should be high enough to ensure a sufficient proportion of total nitrogen to be denitrified and maintain a sufficient MLSS concentration in the anoxic zone. But the recirculation ratio should not be too high to disturb the anoxic environment for denitrification. This recirculation ratio is recommended to be 3 to 5. Thirdly, the mixed liquor in the membrane tank needs to be recirculated to the aerobic tank to avoid overconcentration of solids in the membrane tank. The recirculation ratio is recommended to be 4 to 6, such that the MLSS concentrations in the membrane tank and the aerobic tank are at a ratio of about 1.2 to 1 according to mass balance. Here, these equations show the mass balance of mixed liquor between different tanks, which is influenced by the mixed liquor recirculation. We can see that the MLSS concentrations between different tanks are proportional by a factor related to the recirculation ratio. From the recirculation ratios, we can calculate the recirculation flow rates of the mixed liquor between different tanks, which are proportional to the flow rate of the raw wastewater. The larger recirculation ratio, the larger recirculation flow rate. Proper pumps with adequate flow rates should be selected to fulfill the requirement of mixed liquor recirculation. The next step is to design the excess sludge production. It can be calculated by 3 methods. The first option is to calculate from the synthesis yield of biomass. According to the mass balance in the system, the excess sludge production, which is the net production of sludge, is equal to the biomass synthesis from BOD minus the endogenous decay of biomass plus the conversion from influent solids. Here, delta X is the excess sludge production rate. Y is the synthesis yield of biomass. Kd is the endogenous decay coefficient for MBR, which is considered to be larger than that of CAS. X is the weighted average of MLSS concentration. The lowercase y is the ratio of MLVSS to MLSS, which is normally lower than that of CAS. Because of the higher degradation of organics and the higher membrane retention of inorganics in the MBR system. The lowercase f is the conversion rate of sludge from SS. SS0 and SSE are the feed and effluent SS concentrations of the biological system, respectively. In addition to this rigorous calculation based on mass balance, there are other options to roughly estimate the excess sludge production. The option 2 is to calculate from the observed yield of solids. Here YT is the empirical observed yield of solids from BOD, which is considered to be slightly lower than that of CAS. This option offers a convenient estimation during practical operation due to its simplicity. Another option is to calculate the excess sludge production from sludge amount and sludge age, or SRT. This option adds to a retrospective analysis of the engineering data. Here, Vt is the total volume of all biological tanks. X is the average MLSS concentration, and zeta T is the total sludge age, or total SRT. The MLSS concentration of MBR, typically 6 to 15 grams per liter in the hollow fiber membrane tank and 10 to 20 grams per liter in the flat sheet membrane tank, is much higher than that of CAS process. This is due to the complete rejection of MLSS by the membrane and the long SRT of MBR. The total SRT of MBR is normally in the range of 15 to 30 days, which is typically longer than that of CAS, 10 to 20 days for example. This is because the membrane can completely reject suspended solids, which enables complete decoupling of SRT and HRT. In other words, the SRT can be extended without extending HRT. A longer SRT facilitates the accumulation of nitrifying bacteria and increases the phosphorus content in the excess sludge. The results of calculations using these different approaches can be compared for mutual verification. It should be noted that when chemical agents, such as aluminum or iron salts, are added to the biological unit for the purposes of phosphorus removal or membrane fouling control, the excess sludge will contain chemical precipitates or coagulation products. The increased amount of excess sludge can be estimated to be 5 times the mass of aluminum or 3.5 times the mass of iron. The excess sludge is usually pumped out from the membrane tank because the MLSS concentration is the highest in the membrane tank. The average flow rate of excess sludge, QW, can be calculated using this equation, which can be used for the design of sludge discharge facilities, such as the selection of sludge pumps. Now, let's move to the next step, to design the aeration demand for biological reactions. The net oxygen demand for the aerobic zone can be calculated according to this equation. It is comprised of the oxygen required for organic carbon oxidation and nitrification, and the oxygen demand offset due to denitrification and mixed liquor recirculation. The offset occurs because denitrification consumes part of BOD, so that the equivalent oxygen demand should be subtracted from the oxygen required for organic carbon oxidation. Also, it should be noted that the aeration in the membrane tank, usually in the form of cross-bubble aeration for membrane scouring, can lead to high DO concentration in the membrane tank. Through mixed liquor recirculation, this part of oxygen will be brought to the aerobic tank. This part of oxygen should be deducted to avoid overestimation of the oxygen demand. Therefore, the next oxygen demand for the aerobic tank is expressed in this equation. It is equal to the demand for organic carbon oxidation and nitrification, minus the offset for denitrification, and the supplement by mixed liquor recirculation from the membrane tank. Here, the volumetric terms represent the correction for mass balance. The oxygen demand for oxidizing organic carbon can be calculated according to the consumption for BOD removal, subtracted by the offset due to utilization of BOD for biomass synthesis. Here, 1.47 is the ratio of ultimate BOD to 5-day BOD. 1.42 is the equivalent oxygen demand per unit biomass. Delta XV is the rate of biomass discharge from the system. Similarly, the oxygen demand for nitrification can be calculated according to the consumption for nitrification, subtracted by the offset due to utilization of nitrogen for biomass synthesis. Here, 4.57 is the oxygen demand per unit geldow nitrogen. 0.124 is an empirical estimation of the nitrogen content in the biomass. Then, the offset of oxygen demand for denitrification can also be calculated from mass balance. It is equal to the BOD equivalent consumed for denitrification, with the nitrogen for biomass synthesis deducted. Here, 2.86 is the oxygen demand offset per unit nitrate nitrogen. Finally, the oxygen amount brought by the recirculated liquid from the membrane tank to the aerobic tank can be estimated as a product of recirculation flow rate and DO content. The DO concentration in the recirculated flow is typically in the range of 4 to 8 milligrams per liter. Now we have obtained the net oxygen demand for biological reactions in the aerobic zone. For further design of aeration facilities, we need to convert the oxygen demand to the standard state amount at 20 degrees centigrade and 1 bar in clean water, based on the local altitude, water depth, temperature, designed DO concentration, and oxygen transfer in the mixed liquor versus in clean water. Here shows the equation for the standardization of the oxygen demand. This equation is comprised of temperature correction, pressure correction, sludge correction, and DO terms. The average DO background in the aerobic tank is typically at the level of 1 to 2 milligrams per liter. Alpha and beta are empirical parameters to correct the sludge condition compared to clean water. Specifically, alpha is the ratio of the oxygen transfer coefficient in the sludge to that in clean water, and beta is the ratio of saturated DO concentration in the sludge to that in clean water. The alpha factor is a very important correction factor for the mass transfer of oxygen in the sludge, which is critical to the design of the aeration amount. The alpha factor can be expressed as a function of sludge concentration, as shown in this equation. The higher MLSS, the lower alpha factor, which means that the suspended solids can restrict the oxygen transfer for biological reactions. It has been reported that the value of the alpha factor in full-scale MBRs is generally higher than that in CAS processes at the same MLSS concentration. Finally, after we determine the standard state oxygen demand, the operational air supply can be calculated according to the efficiency of the aerator. For example, a blower or a mechanical aerator. For blower aeration, the air supply is expressed by this equation. The result can be used for the selection of aerator pumps. In summary, the design of the biological treatment units of an MBR process mainly includes selection of design parameters, calculation of tank volumes, recirculation flow rates, excess sludge production, and aeration demand for biological reactions. In this section, we took the AAO-MBR process as an example to show how to design the biological treatment units step by step. Following these steps, you may also perform the calculation yourself. Have a try.